What is up, everybody? Hope you guys had a good weekend. Today I'm going to be doing my usual Sunday video where I go over maybe some new things in the language or I answer questions and or respond to comments. And I thought it might be interesting to kind of see where I am in terms of the state of the compiler, as well as give you guys a pretty good insight into my intentions with this compiler, as well as the state of my language and where things are going to kind of be moving going forward. So first, I'm going to start off with talking about the state of my standard library. So as you know, I've been rewriting the standard library, and originally I was writing the Bootstrapper, and that's why I went on this huge break because it was very slow. So currently, my standard library is pretty small. I have just the basic things. So I have some pretty basic classes. I have an object class, which represents the highest level class for every class inside of the language. So pretty much every class inherits this class by default. And yeah, so there's that. I also have, I'm sure you guys saw before, I have a primitives file or a primitives class, and that kind of just has all the different primitives that my language supports. And because of the improvements that I've made to the language and to how the compiler processes information, especially generics, before I kind of had to, for my primitives, I kind of had to do this thing where I had a base integer class, which if I go to it right here, and it had like the var representing the value, and then it had some base level functionality. But then I had to individually write out all of the functionality for every single type of native type that Sharp supports. So of course you have your longs, your short, ints, chars, and everything else. So because of pretty huge advancements in language, you can now see that it's very simple to just create a bunch of classes. And I now support these values as native types. And effectively, what that does is it does exactly what you expect. So this is going to be an int 64 that's represented here. So any code that's going to be inside of this base class that uses the native type, it sets the value to that type, and then any operations that happen on that value are going to happen as you expect. So if you try to assign, I don't know, let's say we have like an int 8 and we try to assign 1 billion to this value, well, the value is going to end up wrapping over however many times to fit into the size of this integer. So that's one reason why this is a lot cleaner and a lot easier for me to write as well as understand as well. It's pretty cool. So I also want to talk about the state of my compiler. So as you've seen before, like it's pretty obvious. Uh, I have a lot of code that's commented out, and I have more specifically statements. You can't process statements yet in the actual language. So let's jump into my compiler and kind of see where I am. So obviously my optimizer and code generator aren't done yet, as you saw in a previous video I did. That's why I wasn't able to create the slide for that so I could show you guys, but the front end is completely finished. So the front end is going to basically represent the parser, which I'm going to be going over the next few weeks on how to build a parser from scratch. You guys already saw how to build a tokenizer fully. And of course, we have our error management system, which is already done as well. But when we go to the compiler, things get pretty interesting. So I created a lot more folders here. This is a lot more complicated than my previous compiler. So if I go to my old grammar, which is the old compiler, I'm still copying and pasting code from here and reusing old stuff. But you can see all I had was just a parser, which contained the front end part of the actual compiler in one folder. And then this was effectively the entire compiler. But now the compiler is a lot more complicated, so I have quite a bit more code, and I'm nowhere near done. So, I mean, there might be some more files added here later on, but yeah, you can kind of see it also makes it a bit easier too in terms of structure to understand what's going on. So with my compiler, so I'm going to do a search here. I'm going to search for compile, and this basically represents the entry point of our compiler. So once we're compiling or once we start compiling, we pre-process everything in the code and we post-process everything in the code. So what that basically does is, in short, as you're processing your file, you need to figure out what everything is. So I'm going to go into this in further detail later, but this is mainly used for generics. It's used so that if you have an inferred type system, you need to be able to pre-process and post-process all of your code to be able to figure out what this is. Now, it's easy when it comes to numbers, but like let's say we had here, I'm going to delete this. I'm going to create a class called car, and it's not even going to represent a car, but I'm just going to create some class. And let's say we have a variable called x, and we assign x to y. Well, what's y? Because I have an interpreted or a inferred type system, I can say y is equal to z. Well, what's z? And then I can say z, function z, and then I'm going to create a value field, and I'm going to assign that equal to 9, and I'm going to assign a getter, which is going to return value. So as you guys know, and I've explained this in a previous video, but as you guys know, I support getters and setters in my programming language. So you can basically create a field called value. You can assign it a number or whatever. And I think I actually have to type return here. But you can assign value a number and you have a getter and setter. Now what this does is this effectively creates a define get underscore value function here. And this function basically just pastes in the code that I wrote up here. So whatever code was written in these brackets gets pasted into the code that was injected into this class. But as you can see, this is pretty complicated. Like you have a variable called x, you have to figure out the type of x by inferring the type of y. Well, you have to figure out the type of y by inferring the type of z. And once you get to z, then you have to say, all right, well, get value. Well, that doesn't exist in this class, but it actually does. So then you have to find the field value. So you look for the field value, you have to infer the type of value. Okay, so you get, that looks like a 9. Now you have to create the getter for the actual field value. And then you have to reprocess this expression again and call the function. Okay, now we have the type of z, we assign that type to y, then we assign that type to x. So this is really messy, again, like I said, but that's one of the main reasons why you have that. Now, in my humble opinion, I believe that if you actually wrote your compiler correctly, and especially a compiler of this magnitude where you can have something so complicated as this in your language, I would say about 70% of your compiler should be written by the time you get to the compilation stage. Now, I'm not going to go too much into detail about why that is or how that works in this video. We're going to talk about that in a later video. Once we get done with our parser, I'm going to revisit this topic and talk about why 70% of your compiler should be done by the time you get to the compilation stage. But in short, I'm going to show you here. If you guys notice, I'm on line 7,457, and I'm not even at the bottom of the file. So if I scroll all the way to the bottom, this file is almost 8,000 lines of code just to allow me to pre-process and post-process my, like, everything in the language. So that's what I mean when I say 70%. So let's just jump into it to see what happens. So to pre-process everything, you want to pre-process your classes. You want to figure out all of your generic classes in your language. You want to pre-process enums, variable declarations, aliases, function prototypes, and so on and so forth. You also want to figure out what base classes everything implements. So does car have a base of list of type, I don't know, var? So does it implement this as a base class and represent it that way? You want to do that to make sure that's all good. So that way, if you do anything with type inference and you're using a field that's a car, you know that it also represents that list as a base class. After that, we want to do post-processing. So everything happens for a reason and everything is specifically in an order for a reason. So you want to pre-process your mutations, which we all know what that is. You want to inherit your respective classes, which all that does is that inherits the enum class and the object class. So for every regular class, each class inherits the object class if it doesn't have a base class, basically. And that's how we set up our hierarchy. And then if you have like enum called color, this enum is going to inherit the base class of the enum in my support library called, where is it? Here it is. So it's going to inherit, all enums are going to inherit this class. That way we can add support for getting all the enums, getting the name of the enum, getting the value of the enum, so on and so forth, and be able to have all that support there for that. So that's really cool. You're also going to want to, let's go back. We also resolve all methods, delegates, we resolve all the fields, we inline things that need to be inlined, and we post process our generic classes. This is really complicated, but literally these, what is this, like 7 functions or 8 functions? These 7 functions encompass about 8,000 lines of code almost. So it's pretty complicated, but I thought that this was important. So now I want to make a important mention. So I'm going to go to my parser and go to parse statements. So statements aren't finished. So if you look here, I have a few statements. I have return statements, if statements, switch statements, but the majority of my statements, like try catches, throw statements, do while statements, most of this code is not implemented yet in my parser. So when we start getting into the parser, we're probably not going to get to parsing statements yet, and that's totally fine. In your programming language, you don't need to worry too much about statements. I mean, you want to have your grammar there to know how everything looks, but in my opinion, to when you're starting off, you want to focus on the big things. You want to focus on making sure you can process classes, variables, functions, type inference, class inheritance, polymorphism. There's thousands of things you need to focus on. So that's kind of why when I was parsing my statements, I just stopped because I realized that I had bigger fish to fry. So yeah, once we get to this section, we're probably just going to skip it. I also want to mention something that I don't think I've ever talked about in my programming language before. I received a question regarding processing large files. So there's a lot of nuances that I'm doing in my language, that things that just are, they could be better done. Like for instance, I literally right now have, where is it? There's like a string map. Yeah, so I literally have like a list of strings, and let's say the user just, I don't know, they keep creating a bunch of strings. So they say like hi is equal to this string plus this string, right? And then they just keep doing this. And let's say they ended up copying and pasting this like hundreds of thousands of times. Well, the virtual machine or the actual compiler is going to create 100,000 strings. That's just the way it works. Um, and obviously, if there's a string that is the same as the last string, it's not gonna like create it more than once. So like if I had like something like this, so hi, hello, and then hi, the compiler is going to effectively create 2 strings here because both hi and hi already exist. So it's going to create 2 strings. So each string would have to be completely dynamic in order for the compiler to add it to the string list. But even still, like the user can just say, 1 hi, 2 hi, 3 hi, um, and like, it could really get ridiculous after a while. And here's an important thing that I want you guys to realize. The intention for this compiler is for it to be short-lived. So currently you see that there's a version 0.2.805. This is expected to be the next name of the next version that I'm going to put out when my language is ready. So I'm going to go here really quick and I'm going to show you guys something. So if you noticed, I have multiple releases here, and the last release I did was September of last year, and that was 0.2.587. And if you notice, you can see here 0.2.587 is this. So I'm still copying, because I'm rewriting the entire standard library, I'm copying over stuff from here to this new one, so that's why I haven't deleted the folder yet. But this is the next version of the language. Now, the intention, the true end goal of this programming language is whenever you're building a language, I think that it is important for you to go from language dependency to bootstrapping as quickly as humanly possible. What do I mean by that? Basically, I have this compiler, right? It's written in C++. The compiler is eventually going to generate files that look like this. So I'm going to go here to compiler, and I'm literally just going to say it's a text file. So, I mean, obviously, no one understands what any of this means, but this is a generated output, and you can see here like all these different strings and stuff. I have a solution for this, which I'm going to talk about in a few minutes, on how I'm going to compress strings, because that is a big issue with the programming language. I also have some other issues that I want to talk about as well. But just know that I'm going to also show you this. So sorry if I'm bouncing around. This is a bit impromptu. Also, if you notice, if we go up here to the roadmap, you see that this is version 0.3.0. So the true intention for my language is to build this language back up to a very strong state. So 0.2.805 is going to represent what's called the kernel. And the kernel in every programming language is the starting point at which the program is able to depend on itself. It's like the true kernel portion of the language, the thing that you need to make it work, to solve the chicken and the egg problem of how do you program in a programming language that needs to be created and how does it compile itself and all of those weird things. So that's what 0.2.805 is going to represent. And then once 0.3.0 comes out, Sharp will no longer be compiling in C++. It will be compiling in the language itself. So that's why certain things like, if you notice like strings in the compiler, they're very inefficient how I'm handling them. Or like I got another comment talking about what if the user processed a giant file? Like what if they had like a 4 GB or 2 GB file? In my opinion, if you have a piece of code that's greater than a gigabyte, I mean, who does that? If I'm just being honest, like who writes a 1 GB sized file that's written in Java or C++? I've never seen it before. Correct me if I'm wrong, but in my humble opinion, I think that's a bit excessive. Now, I understand like if you are processing a ton of files, it could get inefficient based on all the things that I'm doing and they're stacking up and it's just slowing down the compilation process unnecessarily. That is true. But overall, what I'm trying to get at is that these little flaws that are going to be here and there are not really going to be something that I'm worried about because they're all going to be fixed in 0.3.0 once the language is able to depend on itself. So let's talk about my solution for string processing. So if we go here, where is it? So if we go to this compiler, right? I mean, you can see there's tons and tons of strings here. And I have some metadata about it here as well, about how to process the strings, what the size of the strings are, so on and so forth. Um, but my solution for that, and I actually just wrote in the roadmap today, is this. So I'm going to add, and you can see it's green, which means I still haven't committed it yet, but I'm basically going to just add string compression to output files. So the format's going to go as follows. You create a chunk, and I have a string compression library in my code. So if I go to util zip. This is the string compression library that I use so I can compress like files. Let's see if I can actually find the actual, here it is. So I can do things like I can compress files, I can compress and decompress buffers and strings and stuff. It's really nice. So basically my plan is to compress the string and have effectively the length of the string, have like some breaker or some divider, and then have the actual string, and then have a delimiter, which delimits the actual strings from each other, and then have the length again with a divider, the actual string, so on and so forth. So I'm basically going to create a CSV file if you want to think about it in simple terms of all the strings, and then I'm going to compress them so that way the size of the executable is not that big. Now, this doesn't really help when you're actually compiling it, and I understand that, and I will have a solution for that that's not yet implemented yet, and we'll talk about that a little bit later. But at least this will solve the issue where when you output it into the file, you won't have this unnecessary like, creating 100 or 1,000 lines of code where it's just making the file larger than it really needs to be. Next, I want to talk about what the language will support. as well as the way that the language runs now. So currently the language is built for 64-bit CPUs. So I'm going to go here, let's see, what is it called? Is it called opcode? So I have a opcode file where my virtual machine, now this is very low level. We're going to get into this later, but I have basically a bit layout for all of the different types of classes for every type of instruction. So the way that I figured this out is I took this calculator, and if you guys never knew about this feature, you need to use it because this is the only reason why I was able to do this. So there's a programmer section in the Windows calculator. Not sure if iOS has this as well, but if you click that, you can click this little thing right here, and you can get a bit layout, and you can change the size of the bits that you're processing, and you can just like fill it in with whatever data you want and see what the actual number value is. You can see the hex value, the octal value, and the actual binary output. So that was really cool, and that actually helped me figure out how to lay out everything. And basically, I have multiple different types of instructions. So I have E class, D class, and C class. So E class instructions are really big instructions where you can pass like gigantic numbers um, into the actual instructions, and each instruction has like, size limits and boundaries for what you can pass. But basically, what these instructions were built under is they were built under the assumption that you're running on a 64-bit PC because the width or the size of these instructions are bounded by a 64-bit CPU. So, or a 64-bit RAM computer, or you know what I mean. So I do plan to support 32-bit, which is DWORD. QWORD is short for 64-bit operating systems. DWORD is for 32-bit. And I do plan to support 32-bit, and I'm going to do a conversion from 64 to 32, and it's going to be a lot of work. But yeah, I just wanted to share that with you because I know that's going to be a question coming up later on when we start working on the compiler. So just know that currently my processor only supports, or my language only supports 64-bit. Now, in terms of what I plan to support at the end of this series, I plan to basically support 32-bit Windows, 64-bit Windows, and 32-bit and 64-bit Linux. And those are going to be under the x86 processors. So if I go to runtime, I can go to my, where is it? So I have right now x64, which is 64-bit assembler. And what that is this is for my GIT. Basically, I write out some code here, which is basically fillers. So that way, depending on the processor you're running on, it will generate the appropriate code. But if you can see here, I literally in my GIT file or in my GIT class, I say if it's a 64-bit, and the OS ID is Windows, then create the assembler. Otherwise, the processor is unsupported, and yeah, and then it won't work. Otherwise, if it's not even 64-bit, then my JIT doesn't support it at all. So eventually, I'm going to show you guys how to support both 64-bit and 32-bit Windows and Linux, but again, we'll get to that a little bit later. But if any of you guys are running or following this series on a Mac or a PC, it should work with both. Um, Probably when we get down to stuff like this, like when we start writing JITs and we're writing actual instructions for the specific processor, it's only going to be used for very specific processors. And if your computer doesn't have that supported, then it's probably not going to work. But for the majority of the series, you should be able to follow along because all a compiler is it's just a collection of C++ code. So compiling down this to your computer's processor won't be an issue. It's just going to be a little bit more challenging once we start getting into actually compiling real CPU code. Also, one other thing that I felt like I should mention as well as a final note is in my programming language, everything is represented as a double. So the way that my programming language works is vars. So like this number, I know you guys have seen like I have the type var, and then I also know that you've seen that I have in my primitives file, I have like uint64, 32. The reason why everything's a double is because if I were to do an operation like this for 64-bit ints, 16-bit ints, 8-bit ints, and so on and so forth, I would have to write individual instructions to process that data type, and it would just create a huge amount of workload for me to have to generate all those instructions. Because if we look currently at my opcode file, I'm already pretty, I don't want to say tapped out, but I do have quite a bit of instructions for my virtual machine. And if I were to add support for processing multiple different types of ints, I mean, this would probably be whatever this is times 4. And I have a limit. So I have a limit based on the way that I laid out my bits, where the max opcode is 255, I think. So let's see if I do this. Yeah, so this is the max length, so it's 8 bits. That's why you see 1 through 8. It's 8 bits, and that's the count of the bits. So you can just like highlight it and see what the count is. I don't know why I didn't just put ones and zeros here, but I have a limit. So that's just a language decision that I decided to make. And basically, in short, what I do when I'm processing int64 is whenever you assign an int64 variable, I would just basically call this move u or move 64 value, and I would basically just cast it to assign that value. Again, we'll go over this later. This is really advanced. I don't want to get into this right now and confuse everyone, but that's just a language decision, and I hope you guys can understand when it comes to building programming languages, you have to create trade-offs. You can't do everything all at once. You can't fix or solve all the world's problems. You have to figure out which issues you want to solve and which ones you want to ignore. And this was one of those areas where I thought that it wasn't that big of a deal because computers nowadays have so much RAM, so much memory that memory really isn't the issue. Speed is more so of the problem. So I made this decision with the idea that memory from now and even going forward is just going to become less and less of a problem, and speed and multi-threading is going to be where you want to focus it on. So that's where I put most of my attention. Although, even though I am putting my attention more towards speed and multi-threading, as you guys saw, I did implement a change to basically drop down the size of all of my objects in the actual programming language. So I did make a change for that because I thought that that was important to do. But again, at the end of the day, I'm really just focusing on making this language fun to code in, making the language fast as possible, making it easy to do multi-threading and thread synchronization, so on and so forth. So that's it for today. Hope this helped you guys kind of understand a little bit about where I am in terms of the state of the compiler. Maybe I answered some questions, maybe I didn't. If you have any more questions, definitely write them in the comments below. But yeah, so and as per usual, if you guys would love to help out the channel, of course, you can go to github.com/androidevcd/sharp. Definitely watch, star, and fork the repository. That gives the language a lot more visibility and lets people know that the language exists. Also, if you guys want to stay up to date with anything happening on the language, definitely go to the remastered branch. I update this one almost on a daily basis. It's the most up-to-date branch. Anything other than master and remastered are stale, so don't look at it. And if you guys would also like a more detailed understanding of what's going on, definitely check out the doc folder. You can look at the roadmap for things that I'm looking to add to the language. This is also updated very frequently. And this will contain everything that I've either done with a checkbox or are still working on without a checkbox. Also, if you want to see in very great detail on the improvements that I've made for each version of the language, you can definitely check that out in the changelist file as well. So hope you guys enjoyed the video. Definitely like, comment, and subscribe if you guys like what you saw and you want to see more. Until next time, I'll see you guys later.